Hey there, Stat200. So this office hour I'm going to be discussing simple linear regression. This is our final lesson that's going to be appearing on our midterms and our finals for the class. So let's get through this. This has got some really interesting information. It's a lot of information, but I'm sure that I'm giving you a pretty decent overview here of what you may see on the quiz. And I'm sure if you take a look at this and you give yourself that time to practice, you'll be able to do pretty well here. So, I've started with a practical, a more applied question here. It says, click on one of the following links, and these are links in the quiz. It's Minitab data or Excel data. We don't really use this anymore, but the Minitab data is something you can use. Open that data set. From the data, use the software to answer the following. So first, what's the correlation between SAT Math and SAT Verbal? And second, what is the slope of the regression equation when using SAT Math as the response variable, y, and SAT Verbal as the predictor variable, x? So we're looking for these two quantities. The correlation between the two variables, and then the slope of their regression equation. So I've got a little link right here. This link will take you to a short video that shows me doing this example. I've also posted this link in the Lesson 12 folder, so you can go check it out there if you're unsure how to do that in Minitab Express. Once you do that, though, you're going to get output that looks like this. Now, you'll notice that this says analysis of variance. It looks very similar to an analysis of variance table because that's essentially what it is. Now, you do have something that's a little bit different. When we were doing an analysis of variance, we said basically we needed to have a continuous response, a continuous quantitative response, and a categorical variable as a predictor with more than two categories. Right? That's what we were saying before. And now we're kind of extending the same concept to quantitative response and quantitative predictor, quantitative explanatory variable. And a lot of this looks exactly the same. We have degrees of freedom, the adjusted sum of squares, adjusted mean squared error. We have the f value. We're using the same kind of test to get our p-value here. And we can use this. We're going to use parts of this later. I just wanted to show you this so you get the understanding of what you are looking at. We're going to use part of this on a later question, and I'll get there in a minute. We've got model summary, so this kind of gives us a whole bunch of things. I think the most useful is r squared. Now we're going to use r squared in this class, not r squared adjusted. R squared adjusted is something we use to correct for the number of predictor variables we're using. However, in simple linear regression, we're really only going to be using one. So we're going to just stick with r squared. Then we've got coefficients, so this tells us in our regression equation the term constant is basically another term for the intercept, if you're familiar with slope-intercept line notation. Here's the slope-intercept line notation. So you see that the constant coefficient appears right here. In the SAT verbal, now this is the slope. Now this appears right here in front of SAT verbal. And what we have here are, they're good things. They're basically, right here we're being told what's the standard error of these coefficients. So, you know, we say that this is 224.6, but, you know, that could be off more or less by some amount, right? And this is the amount that it could be off by. So, we also have the same thing for SAT verbal, the slope here. We have the slope estimate, and then we have the kind of demonstration of how sure or unsure we are. And this equates to a t-value and a p-value. Now what these are testing is whether or not these coefficients could truly be equal to 0. So that's the null hypothesis there. And that's that the p-value corresponds to, is that these values in the population are actually equal to 0. And we see that for both of these we have values that are very, very, very small, much less than 0.05. So we're going to reject that null hypothesis and say no, in the true population of all people who take the SAT, the slope and the intercept are both significant for the regression equation. And here's where you get that. So let's scoot back up and see what we can answer. The easiest thing is probably to answer the slope, because that's given to us directly right here in the regression equation. And the way to remember this, the way I learned this when I was in, I don't know, middle school or something, was it was y equals b plus, that's a plus, work with me there, mx, or y equals mx plus b, depending on how you order it, but the way that Minitab orders it, it looks like this. So we see that y corresponds to the response variable, x corresponds to the predictor variable, m is the slope for the predictor variable, and b is the intercept for the regression line. So when it says, what's the slope, we just need to look at this right here, 0.64944. And when we go up here and we look at the slope, there's only one possible option for that. So that tells us right away, A is our answer. But I also want to go over how to get the correlation, because there are multiple data sets that could be given to you and different questions that may have duplicates of slope. So I want you to be able to get both. So we already went through the slope. We just go to the regression equation that Minitab gives us. We find what's in front of our predictor variable. That's our slope. Done. Easy. Slightly more complicated, but not terribly complicated, is finding the correlation. Now the correlation we often write as R. So we say the correlation is R. Now you'll notice that right here we have R squared. So what you can do to find R, if you have R squared, is that you just take the square root of it. So R, the correlation, equals the square root of R squared. So what do? We go to our calculator and we tell it take the square root of 0.3858, and that should give us our correlation. Now if we do that, go to our calculator, we're going to find that this is approximately equal to 0.6211. Alright, and that further confirms that selection A is the correct answer. We have a match on correlation, we have a match on slope, which comes from, well, right here, as well as a little bit further down. So that's our answer. So that's how we're going to work with the output that Minitab gives us to find the correlation and the slope of a regression equation. Alright, let's move on. If the correlation between a response variable y and an explanatory variable is negative 0.4, what's the value that defines how much variation in y is explained by x? Well, I kind of just hinted at that. So this quantity here that defines how much variation in y is explained by x, that's actually just r squared. So we're looking for what's the value of r squared here. Oops, I meant to write a 2. There's a 2 and there's a question mark. So we want to know what r squared is. And all we're given is r. That's the correlation, right? Well, that's pretty easy. We're just going to do the opposite of what we did last time. We're going to take negative 0.4 and we're going to square it. So what's that squared? Go to the calculator, or if you can do it in your head, great, do that. You're going to get a value of 0.16, right? Now if you square a negative value, like I'm doing here, can that square ever be positive? The answer is no. We're not going to be using imaginary numbers. I'm not saying that term in jest. That's a real term. If you're not familiar with it, it's okay. But whenever you square a real number, like this one, even if it's negative, you're going to get a positive answer. So we have some tricks here. We have 16%, 4%, negative 16%, and negative 4%. So they're trying to trick you. And by they I mean the person who wrote the quizzes, which by the way I don't write. I get those directly from the Penn State course coordinator. So what we have here is the r squared. And when we think about this in terms of percentages, remember percentages is just when we multiply any decimal, any percent, or any proportion by 100. So the answer is going to be 16%, right? This value here is r squared. We are given r, so we simply square that value. We find r squared, and then we think about it in terms of percentages. So we can multiply this by 100 and say, oh, it's 16%. It's not negative 16%. R squared can never be negative. So both of these answers are absolutely incorrect from the get-go. All you need to know from here is that you have to explain, or you have to square the value that's given to you. Okay? Next one. Describe the type of association shown in the scatter plot above. Is it positive linear, negative linear, positive curvilinear, or negative curvilinear? Alright, so let's take a look at what these things are. Positive linear association means that as one variable increases, so this x variable increases, that also the y variable increases. Think about height and weight. As somebody gets taller, you expect them to weigh more, right? On average. Not true for absolutely everyone, but on average. That's a positive association. Now, a linear association means it follows a line, right? Linear line. So here you see that this follows a line. It's not like this, or like this, or like this. It's not curvy at all. It's a straight line. So positive linear association, that's obviously what we have here. A negative linear association is going to look similar to this, but now as x increases, y will decrease. So the line will end up looking something like this, or this. Anything where the slope is negative, right? So it's a negative linear association, a negative association that follows a line pattern. Now a positive curvilinear association is what I was alluding to before. It's any kind of positive association that doesn't follow a line, but follows a curve somehow. You see what I mean? I'm trying to draw these with my little laser pointer as best I can. Negative curvilinear association, similar deal. It's going to go down, but it's not going to follow a straight line. It'll look like one of these kind of curves, essentially. So what do we have here? I already said we have a positive linear association. Now I also want to make a note, when we're talking about association and we're talking about how we measure association with correlation, which is R, can be between -1 and +1, right? A negative R value, a negative correlation, means that our association, or our slope, is going to be negative. A positive one means it goes up. Now, a R value of 0 means that we can't determine any strong linear relationship. And if you go to Wikipedia and you search correlation, there are actually some great examples of correlation equal to 0. But some of them might be, you just kind of have a general blob. When you plot all of your points on a scatter plot, you don't really see a clear line that goes through any of this. You could say, well, maybe there's a line that goes here, but there could also be a line that goes here. It could go here. It's not clear. You don't know. So that's an R value of 0. That's a correlation of 0. A correlation of -1, or let's start with a correlation of +1. A correlation of +1 means every point falls exactly on the line. So if you drew a line, like here, you drew a line, a single straight line can encompass all the points. It's a very rare thing. The only time you see that is when you have what's called a deterministic relationship. So, for example, if you regressed, you used regression for your height in inches and your height in centimeters, you would have a perfectly straight line. Everything would fall exactly on that line because there is a deterministic relationship between how tall you are in inches and how tall you are in centimeters. Once you know how tall you are in inches, without any variance, you know how tall you are in centimeters, because it's a direct conversion. So that's a case where you'd have an R equal to 1. Now, if you have an R equal to 1, that means your R squared is also equal to 1, which means 100% of the variation, 100% of the change you see in your response variable is caused by your explanatory variable. That's what that means. Similarly, with an r of -1, you're going to have all points falling perfectly on a line that goes downwards, that has a negative slope. I can't think of a good example, but there have to be other examples where it determines, I can't think of a good one right now, but I hope that you see my point, is that if you have an r of -1 or +1, all your points can fall perfectly on one line. As you get further and further from -1 or 1, you get closer and closer to this kind of mass or anything that doesn't fit a perfect line, right? You can think of other examples. So correlation only works with linear relationships is another thing. So imagine we have a curvilinear relationship, one that looks maybe like a rainbow, something like this. Now it's also hard to fit a straight line through a rainbow, right? You could say, well, kind of like this, but at the same time it could also be like this. I mean, the best way would be maybe to predict like this, but it doesn't even do a very good job then. So that's when you'd have an r equal to 0. So these are both r equals 0 examples, just to give you a bit of intuition behind the correlation. Okay, enough of that. Let's move on to another way to find r squared. So this has a regression equation for left palm length, which is our y variable, and right palm length, our x variable, for 55 college students gave an error sum of squares, SSE, remember this harkens back to the ANOVA table, of 10.5, and a total sum of squares of 85.2. The proportion explained by x, r squared, is what? Another way to calculate r squared, besides squaring correlation, is to take the sum of squares of the regression and divide it by the sum of squares total. Now the sum of squares of regression is equal to the sum of squares total minus the sum of squares error. So we could rewrite this as the sum of squares total minus the sum of squared error and divide that by the sum of squares total, which you may also notice is the same thing as writing 1 minus SSE divided by SSTO. So that makes it very easy for us, right? You just plug things into the formula. 1 minus 10.7 divided by 85.2. You go to the calculator, you plug it in, and you're going to find that it's approximately equal to 0.8744. There's actually another 4 at the end there. And I ran out of room. But what you see here, 0.8744, matches up perfectly, 87.4%. So that's how you can find r squared when you're given the SSE and the SSTO. Okay, and that's something that does come from that ANOVA table. So if we wanted to look at that regression output from number 1 again, we could also find the r squared that way. It's the same thing. All right. A regression, let's move on to the next one. A regression between foot length, the response variable in centimeters, and the height explanatory variable in inches for 33 students resulted in the following regression equation. Y equals 10.9 plus 0.23x. One student in the sample was 73 inches tall with a foot length of 29 centimeters. What is the predicted foot length for this student? Now this is trying to make sure you really understand what you're doing. It gives you both. It gives you how tall he was and the foot length. But he says the response variable is foot length, and it says what is the predicted foot length. So you're actually not going to use this value at all, right? You're only going to plug in his height to this equation. You're going to plug it in for x. You're going to find out what we think y should be. So if we do that, this ends up being y equals 10.9 plus 0.23 times 73. That's how we do that. Then we go ahead and we plug that into a calculator, and we get a value of 27.69. And perhaps what I will write here is I'll put a little hat on this y, because that indicates that this is a prediction, right? Because we know what his y value is. His y value is 29 centimeters. So this is his predicted value based on the regression equation. We find that we predict his foot length in centimeters to be 27.69. We have a value here. Perfect, that's what we get. So there are gonna be, for sure, several examples where you're given a slope, or I'm sorry, where you're given a regression equation for the line, and you're going to be asked to predict something. Now you have to make sure that you're predicting correctly. You know, if they say, if they don't give you the right thing, if they don't give you the correct explanatory variable, so if they ask you to predict his foot length but they didn't give you his height, you can't do it. You wouldn't be able to predict that, right? So that's really the only trick. It's otherwise fairly simple. Just plug the explanatory variable in place of x and find your predicted variable y. Alright, and finally, which of the following cannot be answered from a regression equation? Remember, something like this. Predict the value of y at a particular value of x. Well, we just did that, so we know we can do that. Check. The slope between y and x, well, we already talked about how the regression equation is the intercept plus the slope times the explanatory. So there's the slope. We know the slope then, so we got that. Check. Estimate whether the linear association is positive or negative. Now, how would we do that based on this? Well, we can. All we need to do to know whether it's positive or negative is see whether the slope is positive or negative. So here, we have a plus sign here, so it's positive, right? But if you had a different instance where this was negative, then you'd say, oh, it's a negative association. So again, check, we can do that. So by process of elimination, the only answer remaining is D, estimate whether the association is linear or nonlinear. And we can't figure that out from the regression equation. We can see what the correlation coefficient is, and maybe if it's nonlinear, if it's something like this guy, you know, maybe we'll have like a surprisingly low correlation, but we can't tell. We can't tell whether an association is linear or non-linear, and we don't really cover that in this class. The only thing that's important for you to know is that regression, as far as Stat 200 goes, is going to be a linear affair. So anything that makes any mention of any kind of curvy relationship or quadratic relationship, anything like that, no, it's not going to work. Okay? So that's a basic skeleton of what you might see on the unit quiz this week. And if you have any questions, as always, please feel free to send me an email. All right. Good luck.